when you want.
Okay, so we're happy to have Baptiste Louf from Uppsala University talk about combinatorial maps versus hyperbolic surfaces in large genus.
Well, yeah, thanks for the introduction and thanks for the invitation also. Yeah, so I'm gonna talk about mostly combinatorial maps and compare these with these hyperbolic surfaces. So these are from very far. Roughly, what I'm gonna do is like compare two models of random surfaces. So there's many ways to define models of 2D surfaces, and then to put like randomness and to study the geometric properties of these random surfaces. What we did in this talk was mostly to study combinatorial maps, which are more our specialty, and then we figured out a quite surprising coincidence involving hyperbolic surfaces. So actually, I don't exactly know what the audience is familiar with and what is everyone's specialty. So this is meant to be like an informal introduction. I know we're not coming from the same world, so I'm just like trying to build a little bridge with you guys. So do not hesitate to like interrupt me at any moment, at any point in time during my talk, if you have a question or a comment or anything. So yeah, well, this being said, so I just mentioned that this is a joint work with Svante Janson, who is a prof here at Uppsala University. And then let's get started. Okay, yeah, I'm gonna start with maps, which is my sort to say area of expertise, and I will try to again give an informal introduction to the world of maps. So if you need more details or if you have questions, do not hesitate to interrupt me. So what is a map? Very roughly speaking, a map is just a discrete surface. So this is how you should think about it. It's just a discretized surface. And more formally, it's just a map is the data of gluing some polygons along their edges to create a compact connected, to create a surface. And in this talk, it's going to be both compact, connected, and oriented. And I am a combinatorist, so I do everything up to homeomorphism, more precisely orientation preserving homeomorphism. So for me, any two triangles are the same, and etc. etc. Like any pentagon is the same. So all I get, basically a map is just, as you can see on the left of this picture, a collection of polygons and a way to glue edges 2 by 2. And in particular, so this is just combinatorial data. So given a set of polygons, there's a finite number of maps that you can create. And so in the study of maps and in geometry of surfaces in general, I'm sure you're all familiar with this. An important parameter that encodes the topology is the genus of the map, which is also the genus of the surface. It's just the number of handles, to say it informally. So that's for the definition of maps, very briefly. And so there's many ways you can study maps. You can enumerate them. You can try to find bijections to like find the structural combinatorics inside the maps. You can put them in relation to statistical physics or algebra. But today we're going to focus on random maps. So the main question is roughly, I'm taking a large random map and I want to say, what does it look like? What are its geometric properties? And in the study of random maps, most efforts have been directed at towards studying uniform maps of the sphere. So I take a uniform, taking a uniform sphere built out of a certain number, given number of polygons, and then I want to study its geometric properties. And I think the main result in this domain is the identification of the scaling limit, which roughly says what does it look like from far away. So you could also see it as now it's a sphere constructed with so many polygons that it looks kind of smooth. So it's the approximation of a continuous surface. And the scaling limit has been identified and constructed. It's called the Brownian sphere. You might also have heard of something called the Brownian map. And here's a picture of this map that kind of reflects the fractal properties, so associated to the Brownian aspect of this object. So that's just for a bit of history. There's obviously much more work that has been going on. But what I wanted to say is like most of the time people were interested in random maps on fixed topology and the topology of the sphere. So random maps of the sphere. Something that has started to be studied in very recent years, and that's what has been my focus mostly in this world of random maps, is the so-called hygenus maps. Now, instead of just taking the size of the map to go to infinity, I also want its genus to go to infinity. So here I'm hiding a lot of things under the carpet. I'm just I'm saying both the size and the genus go to infinity. You need to specify at which rates they go to infinity towards each other. I'm hiding, swiping this under the carpet for now. But when people started studying this map, something was really clear, is that you could calculate easily some kind of average discrete curvature, and it was negative, bounded away from zero, which made us expect that these objects would show some hyperbolic properties in some sense. And we already have a few results in this regime. And an example of such a result in the hygenus map regime is, well, something actually my co-author Thomas Budzinski talked to you about a year ago or something. It's the identification of the local limits of hygenus triangulation. So you take a surface with very high genus built only with triangles, and the local limit by, well, opposition to what a scaling limit is the kind of a different focus. Scaling limit, you look at your object from afar, so you don't see the details. Now local limit, it's the complete opposite. You will zoom in and you will look at what the neighborhood of a point looks like. And so there's a proper notion to define this rigorously. I'm not going to dive into the details, but this is here an image, like a representation of what this kind of object look like, and this local limit looks like. And of course, there's many open questions that remain. This is a very new field. Now that we understand the local properties, we want to understand the global properties of this object. We also want to enumerate this object, because if you want to count things, when there is one parameter, it's quite well understood. When you have two parameters, especially when they go to infinity, it's much harder. So there's still challenges going on, but and this is outside the scope of this talk as well. So I will just leave it here, and let me now precise a bit more what our model is today. So I'm going to restrict to something more, I'm not going to talk about like the whole picture now. I'm going to focus on the model, and the model that we used in the work with Svante Janson. So our model is unicellular maps. So they are maps with only one face, which means that it's a surface built by just gluing the edges of a single polygon. So here you have an example of the torus being built out of a hexagon. And so we want to study random surfaces. And so, as I said, given this a collection of polygons, there's only a finite number of ways to build a surface out of it. And in particular, like for this 2n-gon, there's only a finite number of ways to glue it such that, well, in particular, it has a given genus G. So if you have a finite set, how do you sample something randomly, the easiest thing to do is to sample it uniformly. So now I'm going to say this is a random unicellular map, random map with one face. I'm going to call it UNG. It's so a random map of genus G and of the two built from the two n-gon. And since this map is also a graph on a surface, it's a kind of a metric space endowed with the graph distance, but I'm going to rescale the graph distance by this factor 12g over n, square root of 12g over n. And I want to study the geometric properties of this object as n and g go to infinity in any rate, with the only restriction that the genus goes to infinity slower than the size.
So is the graph distance is something like the number of edges that agree, or?
Yeah, the graph distance is just the shortest path in terms of how the graph distance between two vertices. So the points of my metric space are the vertices, and the distance is just what is the shortest number of edges I have to take to go from A to B.
Oh, okay. I understand. Sorry, I was confusing it with something else. Okay.
Yeah. Sorry. And then, so this is obviously like if you don't rescale the graph distance, the distances can only be 1, 2, 3, 4. They're integers. And here, let me point out that this rescaling in the limit will make it continuous, because this g over n goes to 0. So this is going to make, this is in some sense zooming out a bit. So we won't focus on the very local picture, but we will zoom out a tiny bit because we're rescaling the graph distance. And so that's for our model. Now I just want to talk about the other model that we're connecting maps to. It's hyperbolic surfaces. So I actually don't know how much you guys know about these hyperbolic surfaces. Probably most of you know actually more than me. So, but I mean, I can't know. So I will do my little introduction to hyperbolic surfaces. I'm sorry for those who master it much more than me. So just to recap, a hyperbolic surface is just a surface, a smooth surface with endowed with a metric such that this metric yields a curvature that is constant -1 at each point of the surface. So it looks locally, in other words, it looks locally like the hyperbolic plane. And well, again, something very standard. These surfaces, there's a combinatorial way to build them. Actually, there's a building blocks for hyperbolic surfaces. They're called hyperbolic pairs of pens. And a nice fact is that a hyperbolic pair of pens is just a sphere with three geodesic boundaries. And the nice fact is that for each, if you specify the length of the boundaries, there is a unique hyperbolic pair of pens with these boundary lengths. And in general, for every surface of genus at least 2, compact surface of genus at least 2, you can put a hyperbolic metric. And you can actually put multiple hyperbolic metrics on these surfaces. But if you take a hyperbolic surface, so a surface endowed with a metric, you can decompose your surface into these small building blocks that are the pair of pens. There you can find a 3g-3 simple closed geodesics, such that if you cut along these geodesics, it divides your surface into a set of pairs of pens. I must just point out that this choice of curves is actually not unique. Very briefly, for those who know, it amounts to choosing a trivalent graph, but I'm not up to some automorphisms, but I'm not going to dive much more into this, into details. And what's good with this decomposition is that it kind of gives you a set of coordinates to navigate the big space of hyperbolic surfaces. Because if you want to build, if you give me the hyperbolic pairs of pens, so I want to build my my surface again, what I need to know is, okay, first the length of each of the boundaries of each of the curves. And if I want to build it back, if I want to glue back two things, two boundaries to each other, I just need to understand how twisted they, like the twist factor before I glue them together. And so this determines the surface uniquely, and so you can build up the space of hyperbolic surfaces. It's called the Teichmüller space, and this is thanks to oh yeah, as I've said, all these surfaces compact. Yeah, I'm only talking about compact surfaces today. But anyway, so yeah, as I said, do not hesitate to interrupt me because I might not see the messages in the chat also. But what it boils down to is that this space, the Teichmüller space, is just isomorphic to R plus times R to the 3G minus 3. So it's a very well-behaved space. However, this is not the space of hyperbolic surfaces we will consider. We will quotient this space by the isometries of the surface, saying now I got my space of hyperbolic surfaces that are parameterized by this matrix. But then I'm going to say two surfaces are the same if they're isometric. Again, I'm not going to say what I mean by isometry, but all I will say is that these isometries are not so easy to understand, and it's not something that acts. There is not the same, orbit. They don't behave the same for every set of surface. So basically what you're doing is you take your nice space TG, and since you quotient it, you're like folding it on itself, and it actually becomes less nice. It actually doesn't stay a manifold, it becomes an orbifold. So you might ask, why are we doing this to ourselves? Why are we considering a actually more complicated space? And then the reason I will tell you in 1 minute is that so this is a result due to Weil-Petersson. You can define a volume form on this, well, first on the TG, you just define the standard volume form compared to the, with respect, sorry, to the differential Nielsen coordinate. And it turns out first that this volume form is something called that it's identical to something called the Weil-Petersson volume form, which has a complicated definition. But more interesting for me, at least at the moment, is that, so this is sometimes called the magic formula, because this form doesn't depend on the choice of curves, although the tangential Nielsen coordinate don't depend on the choice of curves. And this form is defined on the Teichmüller space, is well defined on the Teichmüller space, but it kind of descends on MG, so it's still well defined, and there's no contradiction to define it on the moduli space. So that's already good. But the most interesting thing for me is that this, when you descend on MG and you integrate this volume form over MG, you actually get a finite number, whereas you get infinity on TG. So if you have a finite volume, this means I can define a probability measure on my set of surfaces. Yeah, the probability of a subset is just the volume of this subset over the total volume. I just have to renormalize by the total volume, and I'm good. And so this allows you to sample a random hyperbolic surface under something that we call the Weil-Petersson measure. We're going to call it SG. And it turns out that, like, 10 years ago or so, independently, Mirzakhani and Gust, Bari, and Young started studying the geometric properties of this SG as the genus goes to infinity. All right. And do we have any questions so far? I don't exactly know how I'm doing with time, but I might be a bit ahead. So if you have any questions, I'm happy to answer them. All right, well, if not, I will just continue. And so now I define my two models of random compact surfaces. And as you might have guessed, in these two models we study them when the genus goes to infinity, so in the high genus, large genus regime. And what we did with Svante is to study these unicellular maps, this model of maps, and we noticed a very strange conjecture, strange coincidence. We were interested in geometric observables that was to count curves on our surface. And it turned out that we obtain a similar result. So what do I mean by curves? It depends on your model. But it turns out that 4 years ago, or a bit more maybe, Mirzakhani and Petri counted, so simple closed curves, and by curves here I mean geodesics, in this hyperbolic surface, this high genus hyperbolic surface, and they obtained, as the genus goes to infinity, they obtain convergence in distribution to Poisson law with a certain given parameter that's written here, the integral of the hyperbolic cosine. And so last year we did the same with Svante Janson. We counted simple cycles, so now curves for us are just simple cycles of the same length with respect to the rescaled graph distance, and we obtained the exact same result. So we obtained the exact same distribution for these curves, these short curves. So obviously we were a bit surprised, and we are. The natural question is this really just a coincidence? And so the conjecture we can make is in the certain vague version is that these two models are somehow the same, or should like a lot of a lot of geometric properties should match, not only these simple closed curves, as the genus goes to infinity. So these models are obviously not the same for a fixed given genus, but when we go to the limit, they should be the same with respect to some well-chosen metric. And so I must say that for us, the surprising thing was not the Poisson law. The Poisson law is something that's very typical when you count curves on surfaces or cycles in graphs. But the fact that we have the exact same parameter, this is the surprising coincidence. And so this led us to have this kind of conjecture. Yeah, I just want to make a little comment on what I just said. Making the conjecture requires a bit of work, actually. I think we don't have like a super mega precise conjecture as of now. What I believe is that, you know, as people investigate the relation, then we will, you know, like find the right notion, for instance, the right metric that we want to impose on our that we want to with respect to which we want to compare our two models. There's two things that I'm pretty sure of right as of right now. Two things that seem to be necessary. The first thing is that hyperbolic surfaces are smooth, while maps are not at all. Maps are superfractal objects, and so we need to find a way to remove the fractal part. Fortunately, when you're dealing with unicellular maps, the fractal part is easy to identify. So this is what a typical unicellular map looks like. So it's just some core, like something we call the core, with things attached that are actually trees, and these trees are actually the fractal part. Like these plane trees are actually all the fractal part of the map. This is only true for maps with one face. For maps with more faces, it's much more complicated to identify where the fractal bit is, so like to distinguish the fractal and the non-fractal. So, but this this is there's an easy fix. You can take your map and then say it's actually not the map that's going to look like the hyperbolic surface. It's the two core. It's when you shave off the trees. In our case, since we were counting simple cycles, it actually didn't matter because no cycle is going to go through these trees. Also, seen as just a graph with our rescaling, our maps still look like would still look like metric graphs. So like kind of something that is not two-dimensional in some sense. So we need to consider that these maps have an interior, like, and the easy fix is to think that, well, we were gluing a polygon in the first place, so we need to add the interior of this polygon to the model. So we need to see the maps as the gluing of a hyperbolic polygon. So this, if I can give my opinion of where this should be going to investigate this conjecture, this is really the important starting point.
Question.
And yeah.
Oh, sorry. So I'm trying to make sense of what's on the left side, because you have polygons that you're gluing the edges, identifying the edges. What are the trees corresponding to?
Yeah. So if you think it's a good question because it's actually not easy to think about it. So this is just the graph corresponding to the gluing of a single polygon. So for instance, here, what happened? If you try to fill it with a polygon, it means that two consecutive edges of the polygon were glued to each other. Can you, do you see what I mean?
Yeah, I think so. Yeah, I see that. Thank you.
So you glue two consecutive edges and then you start gluing it. Every time you have this kind of like leaf, it means that two consecutive edges were glued. And then from there on, it's in the same principle. This is how you can build trees. So this is like whenever you have a tree, it means that you had like a certain number of consecutive edges which were glued 2 by 2 in some way inside this multiset, you know, like this, without or if you can also think of like if you draw your polygon and now you draw the identifications by lines inside the polygon, it's where it doesn't cross.
I see, yeah.
To build genus, you need to have crossings. Like if you have, if you have a square, okay, this is going to be very ad hoc, but this is, can you see it? I don't know. This is your square. You're going to identify this side to this side and this side to this side. You will have crossings. So this creates the genus. But on the other hand, if you want to create trees, is like just like consecutive edges that are linked to each other without crossings. I don't know if it was enough or too much or or not enough.
It's helpful, thank you.
Okay. Is there a limiting procedure where the limit object is a surface rather than metric space? Yeah, I'm going to talk about this really briefly. Just let me just finish this slide, and then it's gonna be better easier for me to understand you to answer your question. Sorry, Asa. So yeah, so the right metric that we think is best to compare these two models is the Gromov-Hausdorff distance on metric spaces, which allows you to compare metric spaces, so that as the genus goes to infinity, there is a coupling between the two random models such that the Gromov-Hausdorff distance goes to 0. This would already be something good. This transports a lot of geometric properties, but it doesn't make sense of the topology. For instance, like the Gromov-Hausdorff distance doesn't capture separating curves in your picture, in your surface. So Yeah, so the question of Asaf was, is there any limiting procedure where the limit object is a surface rather than a metric space? I don't know if you can have a metric that encompasses everything. I'm not an expert. I must say that I cannot hope for understanding a limiting object for sure, because if you were to find like to understand a limit object with respect to some scaling, it would be highly pathological, because well, even with this rescaling, the diameter still goes to infinity. But on the other hand, yeah, you have very short cycles. You might have pinch points in the end. The topology, or you might have pinch points or pinch lines in your limiting object surface. So it seems to me that like any like kind of scaling limit or half scaling limit would be very pathological and would involve like a crazy amount of math that I'm very far from mastering, and I don't know if anyone has done this. Yeah, so like what I'm thinking more is just like to have these two objects, the good notion of distance and this notion of distance goes to zero, and then we will still be happy, because it means that, yeah, like this transports properties from one model to another. I don't know if this is a satisfying answer for you, Asaf.
Just to rephrase it, what you're looking for is a coupling between the two models.
Yeah. I said it briefly, yeah, but yeah, a coupling and the right notion of distance. The coupling is not it's just a technical detail. The right notion of distance might be more the philosophical and or mathematical aspect.
Yeah.
But yeah, of course you need a coupling, because these are random objects, so you need to understand how to compare these things to couple the probability laws.
Okay, great.
But yeah, so okay, next slide. So yeah, so the hope of this conjecture is nice, and if it were to be true in any sense, it would be very interesting, at least to me, because it contributes to this notion of universality of in the world of 2D geometries, meaning that, well, you might have different models, but they are still like part of a bigger family. They have things in common, and within certain limits, they actually behave the same. But there might also be some practical implications. For instance, if the conjecture is true in a strong enough sense, it means that some of the problems that are still open on hyperbolic surfaces, we can transfer it to map problems. And actually, unicellular maps, they're very nice because they're in bijection with some model of trees. So we will translate these hyperbolic problems into problems of random trees. So this is due to a so-called magic bijection that I'm going to talk about later. But this, I just want to say that this random trees is something that us combinatorists and probabilists, we understand very well. So that would be that might help prove problems from the other side using just combinatorics and probability. So and of course we don't have to wait that the conjecture is proven or to work on these open problems, to transfer these open problems directly on our maps. And for instance, as an example, like in these random hyperbolic surfaces, we know that the diameter is logarithmic, but we don't know exactly the right constant. We know it's between 1 and 4, so the lower bound on the diameter is some deterministic lower bound with considerations on the area. The upper bound comes from spectral considerations. And well, we're inclined to believe that this has to concentrate around 1 single constant because it's what it always does in math. So we don't see why it would not be the case. I would say half of the people guess that the right constant is 1 and half of the people guess it's 2. So that would be interesting to figure out and to see if we can figure it out on our model. We can also investigate some spectral properties like the spectral gap, the isoperimetric constant, and so on and so forth. So again, like the point of this slide is to say this is not only the conjecture like this is not only to look nice, it would be also to be able to transfer problems from one word to the other. Do you expect your results, so as I've asked, do you expect your results holds for random 2 cellular maps? So you mean maps with 2 faces, right? I cannot say for sure, but I think I would be tempted to say yes. I would be tempted to say yes, but just for the reason that I don't have a solid argument for this, but most probably if there's two faces and you don't restrict the sizes of the faces, one is going to be big and the other one is going to be small. And so it's just going to work like it, as if it were a unicellular map plus some like defect, some arbitrary it's most probably going to work the same. I can't be sure, but that's my first intuition, like as you're asking right now. All right. How much time do I have still remaining?
Well, 10 to 20 minutes, depending on how much time you want to leave for questions.
Okay. Yeah. I will be within these bounds. So this was actually a very long introduction and didn't give any idea of proof or anything. I want to just give you some ideas of proof. Again, I don't know what the background of everyone here is, so maybe that will sound extremely naive. I'm sorry. If you all already know all of this is not my intention to offend you. It's just that I don't know everyone's background. So how do you prove this result? So as the reminder of the result, maybe I can show the result here, is that we want to count simple closed curves on surfaces, and we want to establish that this is a Poisson law with this parameter. And how do you do this? How do you prove? The key principle is this method of moments, which roughly says if I have a sequence of random variables and under some reasonable assumptions, if all the moments of my sequence converge to the moments of my target distribution X, then Xn converges towards X. And so I'm a combinatorist, and how do you, in my opinion, like from my perspective, how do you calculate these moments? And roughly speaking, if, for instance, my variable X counts some curves of the given length, then the moment of the moment number R, like X, the expectation of X to the R is just, well, it's just a fraction. It's just like the number of surfaces with R marked curves over the number of surfaces. Obviously, this is very roughly speaking, and it's not properly defined, especially for hyperbolic surfaces, because there's no such number. It's not a finite number of surfaces, but there's something close enough. So for hyperbolic surface, the method of Mirzakhani and Petri goes like this. It's just, I'm going to do the first moment only. I just want to count the average number of closed geodesics in my surface of genus G, and I say I want to count these geodesics with length between A and B. And if I have a geodesic, so little something that I will not prove, but it can be easily proven that if it's short, it's going to look like this. It's going to wrap around the handle and not wrap around. It's not going to be a separating curve, meaning I can cut this surface along this curve, and I will always obtain a surface that has two geodesic boundaries, and so the genus is going to be G minus 1. And so if I apply this principle, if I want to count if I want to count the expectation of xg, then instead of having a number, I just use the volume, so that the denominator is just the volume of the moduli space of genus G, and we're lucky because we can also enumerate or calculate the volumes of. There's also like a space of surfaces with boundaries, so it's just counting the number of surfaces of boundary with two boundaries of G of size of genus G minus 1. This divided by the number of surfaces of genus G. Again, it's not a number; it's a volume, but that it's still the same principle. And so once you have this, well, you can. Mirzakhani had a lot of large genus estimates for this Weil-Petersson volume, so then it goes smoothly. You prove what you want for the expectation, and basically you can do all the other moments, and the Poisson law, the fact that you have a Poisson law, so the parameter of the Poisson law is just the expectation. The fact that you want to prove that you have a Poisson law basically boils down to, again, it's not very formal or rigorous, but it boils down to saying that if I take two short curves that are distinct, that I take them uniformly at random on my random hyperbolic surfaces, if they're distinct, they're disjoint. That's basically the underlying thing. In our model, we don't do the same thing. We don't cut along curves, because if you cut along a curve, then the map, we will have a map with one face and two boundaries, and we want to stay within the world of maps with one face. But there's a very beautiful bijection due to Chapuis, Ferret, and Fusy between maps and so-called C-decorated trees. So a C-decorated tree is just a tree with a permutation of its vertices, so like oriented cycles on top of its vertices, with only odd cycles. And the underlying graph of this C-decorated tree is obtained by merging the vertices who belong to the same cycle of the permutation. So you can see here, if you merge all the red vertices, you're gonna get this big red vertex, and so on and so forth. So the underlying graph of this one is the same as this one. And if I take a random uniform C-decorated tree with n edges and exactly the right number of cycles, n plus 1 minus 2g, the magic bijection in the probabilistic version, is that these two random uniform thing, U and G, that I introduced before, the random uniform unicellular map of size n and genus G, and this T and G, their underlying graphs have the same law. So this one is a graph, and the underlying graph of the map U and G has the same law. So it doesn't preserve a sense of topology, but it preserves the underlying graph. And for us, we do not care, because we're just counting cycles, and we don't really care about a cycle is a cycle. We just want to count cycle. We don't need more information than this. And very briefly, how we do to count cycles, if you think about it, if you go back to the model of trees, I'm sorry, this is going to be maybe a bit quick. I'm sorry if it goes too fast. But a cycle, since you build your map by taking a tree and gluing certain vertices together, if you think what is a cycle, a simple cycle is just, what it was before is a set of paths such that the endpoints get glued together when you do this operation here, where you go from the tree to its underlying graph. So that's very roughly. So, and then we need to estimate the probability that these points are glued together, and then we need to count paths in trees, which is something that we can do we can very much do. All right, I know this was a bit rough, maybe for an idea of proof, but I hope you still can get something out of it. So yeah, just gonna finish with some additional questions. Actually, when you look at hyperbolic surfaces, there is unicellular maps inside these hyperbolic surfaces. It's a Penner's spine construction. You can take a point and then look at the points that are that have two geodesics going two distinct geodesics going to this point. So you build on your hyperbolic surface, you can build a hyperbolic unicellular map. And there is a combinatorial equivalent for maps, for all maps. It's called the Sheffer bijection. And so two constructions in these two different worlds have actually the equivalence to each other. And the natural question is, now there's other construction with like trees that allows to like decompose our unicellular maps into trees, which are simple objects that we can understand. Is there a hyperbolic equivalent? Is there an equivalent for hyperbolic surfaces? I have no idea. And again, the question is maybe not well posed, but I want to throw this idea here. Second thing I want to mention is that Bud and Curien showed very recently that if you take the random hyperbolic sphere, but now with a lot of spikes, a lot of hyperbolic cusps, and you rescale it, you get the Brownian sphere. So the same scaling limit as the maps of the sphere. And so this is actually like a first result towards this universality concept that like maps and hyperbolic surfaces in the limit, they behave a bit the same. So this is something that's proven. This is not a conjecture. This is something solid. So the question you can ask is, can you do the same, but now for the Benjamin-Ishram limit, so for the local limit, do the same as we did with Thomas Budzinski, and the thing I talked about earlier? Can you take a hyperbolic G torus with enough cusps, and you get N and G to go to infinity, and you study the local limit, maybe with the right rescaling? Can you find a Benjamin-Ishram limit of this object? And yeah, I'm gonna skip over the last point, but it's I also have we can enumerate roughly high genus maps, and my conjecture is that there is also a sort of universality not only in geometric behavior but also in enumeration, so that these volumes which correspond to enumeration, they have a very similar expression asymptotically. All right. And I think I'm going to stop here. Sorry for speeding up in the last couple of minutes.
Okay, let's thank Baptiste. Thanks. Yeah, so I'll just open it up for questions.
I have a question. So it seemed like in your formulation of the conjecture and also formulation of UNG, you assumed that G is much less than N, right? As they go to infinity. And so I'm wondering, in the case where they go to infinity but proportional to each other, can you give a kind of some sort of conjecture similar to your first conjecture?
Yeah, so that's actually a great question. Actually, how we didn't bump into this coincidence. I mean, I presented it maybe as too much of a coincidence. What we did, let me go back to the model. What we did is actually we first studied the same question on for when G and N are proportional to each other, because that was the regime that actually we used before, like in every other work. And so what happened, if you look at this rescaling of the graph distance, it does not make sense. I mean, this is just multiplication by a constant. So we just calculated this. We found this law, but then it's discrete law. You know, like there's cycles of length 1, cycles of length 2, cycles of length 3. So it's very hard for me to think of you know, this is still discrete. So what would be the discrete hyperbolic equivalent? How could you make the hyperbolic surface discrete with only integer length? This is something I have no idea about. And
sorry, can you repeat the last few sentences again? I didn't understand all of it. Just like, what is the
so,
difficulty?
like,
But yeah.
what you get is a discrete probability law. So you have only cycles of integer length. So hyperbolic surfaces, they're continuous objects.
Right.
So I know how to take discrete objects and make them into continuous objects because, well, you know, like you make the resolution finer and finer and finer, and then it looks like a continuous object. On the other hand, like taking a continuous object and making it into a discrete object, I have no idea. I mean, maybe I will have an idea later, but like at the moment, no, I'm lost.
Oh,
I don't know.
Yeah.
I have no idea.
Well, so speaking of this, what happens if you just fix the genus and send n to infinity? Can you
What
prove
happens?
some version of your conjecture? I'm not sure what that version would be.
Yeah, so this I'm not sure. I'm not sure that there's a version of my conjecture. What I can tell you is that the cycles in the unicellular map, they're always separating. No, there was non-contractible and non-separating, because otherwise that would not be a map with one face. So this is in fixed genus, so you can prove a lot of things about scaling limits. And you can prove, for instance, that the scaling limit of the object has the same topology as it's supposed to be. So there's no like curves that are going to shrink to make pinch points. So in particular, the size of the cycles should be of the same order as the diameter, which is square root of n. So it's a radically different behavior. I don't know if that makes, if that answers the question at all, but like, yeah.
Yeah.
The thing is, it's not very hyperbolic when you fix the genus.
Yeah, so that's why I'm thinking like, well, if we're allowing, so saying that genus is little o of n makes me think, well, we can make n huge and then slowly increase g, you know, so that it looks, I don't know, maybe not very hyperbolic locally, but of course you're rescaling. So I don't, you know, my intuition isn't very complete.
Yeah, I have no idea. My intuition is that it's hard to give a very convincing or detailed answer. My intuition is that there's not much to get from this, but I don't know, like fixed genus is something well understood, and we haven't, I don't think there's much to say. And also like, it's hard to study fixed genus hyperbolic surfaces, because we have a lot of like high genus asymptotics, and then we have like nice convergences and stuff like this. I don't know what, for instance, what the law is, if we know the exact law of the number of cycles on a hyperbolic 3 torus or whatever. Or I think it gets much easier once you go to the limit. So I don't know if it's something to investigate that will yield interesting insights.
Yeah, I guess what I meant to say is it's kind of like taking a double limit. I mean, what you're doing, it looks kind of like a double limit where you take the limit as n goes to infinity first and then g goes to infinity. But yeah, okay, this is not, anyway, yeah.
Yeah, I understand what you mean. Yeah, sure. I don't know. I don't know. Like, yeah, sorry, like I don't have anything intelligent to say to this comment.
Okay, other.
I had a different question. Do you know what the expected degree is of the graph that you get?
The expected degree of a vertex?
Yeah.
Yeah, it's 2. I mean, asymptotically 2.
Really? Okay.
Because
If you remove all the trees, is it still 2?
If you remove all the trees, yes, because most of the, so basically, where is it? It's going to be either points of vertices of degree 2 and a couple of vertices that are like more, you know, structural to the topology, but then most of them are going to be of degree 3. But still, there's going to be like, in terms of order of magnitude, there's going to be G vertices of degree 3 or more, and square root of n times G vertices of degree 2. So that's more. That's asymptotically more. So that's still gonna be the case.
See, interesting, because I thought maybe it might behave like, because I mean, so if you take a random regular graph of degree D, there's an asymptotic law for the number of cycles, right? But it's like it's like D minus 1 to the K over K. With this thing, it's sort of like the exponent is something like E or something, E plus 1 or something, maybe, right? So I thought maybe it sort of behaved like a random graph of degree, like regular graph of kind of like degree E plus 1 or something like that. But I guess it doesn't. That's not.
Yeah. So there's the average degree is 2, but what you can think about, like actually now we're working on like trying to find a better model, like an easier model, and we managed to find at least a better model that has only one parameter in G, because this if you take out all of these trees, this basically this is just like edge length. You can think of replacing all your vertices of degree 2 by a length on your edge. And as I said, most of the vertices here, the remaining, should be of degree 3. The rest is just a mathematical artifact. It's not playing any role. So you could just think of maps of genus G with only trivalent vertices, and then you get a random length on each of the edges, and it turns out that the right length is just independent variables exponential of 1. So you can, like with this heuristic, this is because I talked with Curien and others who happen to have worked on a similar thing by accident, and then they told me, oh, this should be the law. And then if you take this heuristic and then you take the result number of cycles for the 3 regular graph, you get a Poisson point process. Sorry if it gets too technical, but then you can throw the exponential and this edge length, and this blows up to the right Poisson point process that we also got. So like you can really heuristically recover it. I don't think the model of just random regular graph works. I think you still need to have the fact that it remains a unicellular map, so that the gluing of your edges with the order gives you a unicellular map.
Just to repeat what you said, so to make sure I understood, you said it behaves like a random 3 regular graph with exponential edge lengths, exponentially distributed edge lengths.
Yeah, condition that this graph, because here the graph, they have this, it's actually maps. They're like, since you have like orientation of the, distinguishability of all the half edges, in my opinion, you still need to have the right, the fact that the map, that this is a map with one face of genus G. But then this determines everything. With just one parameter, this determines everything. But yeah.
Thanks.
I have to go, but Hunter
Yeah.
can still stay and be the host. And so, so great talk. Thanks.
Thanks a lot for inviting me. Yeah.